Hi folks, my name is Mickey Rowell. I'll be your presenter on this video tutorial on Bekk Smoothness. Thank you for watching. When I last left off, if you will, I had done kind of a tutorial on okay, how are we going to be able to manage this particular property where we can actually evaluate the surface characteristics utilizing an air leak method. The machining industry or the manufacturing industry utilized, as I mentioned, a air leak tool that they could come up with to determine the air leak around a particular part or through a particular part that would indicate whether or not that particular part would fit nicely into their second stage of the production, and whether or not it was going to be too big, whether or not it was going to be too small. But they have these devices and these gauges that would give them some indication whether or not, if I have a part that's too tight, I'm not going to get any airflow through. If I have a part too loose, I'm going to get too much airflow through. So in order to, let's say in order to transfer that particular technology to into the paper industry, as an example, what we need to do is we need to develop create some scenario where we have an area of low pressure and an area of high pressure that will now allow some type of air transfer to take place. And in the 1930s, it was kind of busy. The earlier part of the 30s, a gentleman, Dr. Julius Bekk, devised a device that he could use to sandwich a sheet of paper in between and create a pressure differential across the surface that we want to measure, create a pressure differential across that surface and actually get air movement from the area high pressure to the area of low pressure. What he was utilizing was a vacuum system that would create, again, much like this device here. I don't know if everyone's familiar with it, but if I evacuate this container here, and I'm going to put a piece of filter paper in here, I'm going to pour my slurry in here, I'm going to turn on my vacuum pump, and what's going to happen? The area in the lab, the atmospheric area in the lab is going to want to seek that lower pressure area, and it's going to draw through that filter paper and through my slurry, and along with it, drag the heavy-duty molecules of water into my container here. So it's dry enough so that I can actually remove it, then I can put it on my dryer, and then I can analyze it. Okay, so Dr. Bekk had decided that he would utilize the same concept in his design. So when he came up with this idea, he had a chamber, much like we have here. He had a vacuum pump, much like we have here. He had a gauge that he could tell just how much vacuum was in this chamber. And then what he did was he created a sandwich. This is what I call a sandwich. He had a platen that was a good, hard, firm platen that was going to help to support the sample on one side. Okay? We need to have another part of that sandwich, my third layer of sandwich. I'm going to put that on the top of this sample. So in this case, we're going to utilize a circular glass platen that has a hole in the center. When I put this sandwich together, if I'm not clamping it with all my force or all the force in the universe, I'm going to be able to create a scenario where my leakage, my air can make a path across the paper surface, through the channel, and into my evacuated cylinder, much like we have in this scenario. If my sample has a lot of undulations in it, I might get a lot of air leakage through my pathway here. If it's a very smooth surface, I might get just a small amount of air that goes through my system. But the key is to support the sample with a firm backing, invert the measurement head on top, create a vacuum on this side of the sheet, so that now I have an area of low pressure in my chamber, and I have an area of high pressure, which is in my laboratory, And once I flip this switch, I have a switch here so that I can draw this down to a fixed negative pressure. I open this switch, and as soon as I do that, what's going to happen is any air path that the air can take, any pathway across the surface of this paper that the air can take, is going to go across the surface into my tunnel, into my chamber, and now I've created a pressure differential and I've created airflow. All right? Okay, well that's all and good, but now how do I quantify that to be able to bring it to my production people and let them use those numbers to make better paper or to continue to make good paper? The way I do that is, as I mentioned, I evacuate, shut off my valve, I evacuate this to a fixed negative pressure. Again, as soon as I open my valve, I'm going to create my airflow. But this pressure inside this chamber is going to change. Because I have an area of high pressure, I have an area of low pressure. This high pressure is going to make its way into this low pressure area, and that negative pressure is actually going to change. So what I need to do is I need to develop some type of a flow rate. So now I draw this down to a fixed negative pressure. Okay? If I open up this valve, now what's going to happen is if I have some topography to my surface that I have in contact with my measurement head, excuse me, I'm going to create a pathway that the air can flow into my chamber. Now it turns out that if I draw this down to a fixed level, always draw it down to a particular negative pressure, and if I open this valve and I allow it to drop down to a predetermined level of negative pressure, I can actually measure the amount of air that flows through here, and that measurement air would be 10 cubic centimeters of air that will pass through here. Now that's good. But what I need to do is, in order to come up with a rate, I need to time that period when I have my initial negative pressure and I reach my lower level of negative pressure that I have calculated to bring in 10 milliliters of air into my chamber. So I evacuate this to my fixed negative pressure. I open up my valve and I start my timer. Okay, once open up my valve, once I have the path flow moving, I'm watching a gauge. My gauge goes from my initial negative pressure to my lower negative pressure that I predetermined that will allow 10 milliliters of air to flow, and I shut my timer off. I'm going to label those, I'm going to name those as the Bekk seconds. The time it takes for 10 milliliters of air to flow across this surface through the channel into the evacuated chamber is my Bekk seconds. So if I have a rough sample, you can guess that I'm going to have a high rate of air that travels through my pathway. That's going to give me a shorter period of time in which I've drawn through my 10 milliliters of air. If I have a very smooth sample, I'm going to restrict the airflow, so it's going to take longer to evacuate and reach my negative pressure, my target negative pressure. In doing that, I now have a value, a number that I can send out to my production people that they can use to gauge whether or not that product is smooth enough for the application, whether or not that product meets the stipulations given to us from our customers. So as an example, I might have one day I might be running a product that is a high gloss material. You can imagine that if I clamp this into my sandwich, I'm going to have a fairly low flow rate into my chamber, and it's going to take me quite a long time. Let's say it takes me 200 seconds. 200 seconds to evacuate 10 milliliters of air across the surface through my tunnel into my chamber. All right, so now I can use that value. If my customer, who I'm trying to sell my product to, gives me samples of their material that they are looking for, and it gives me some indication of what my tolerances are. If I put sample A in here, maybe I'm going to get 200 Bekk seconds. If I put sample B in here, maybe I'm going to get 195 Bekk seconds. If I put sample C in here, maybe I'm going to get 175. So now I know that my customer would accept a range of 175 Bekk seconds all the way up to 200 Bekk seconds. And I can use those numbers to provide to my production people to either maintain or to change the process and make that product that that customer is looking for. So I've got one device that works. I want to build a second device. How do I do that? One thing I'm going to have to do is I'm going to have to maintain all of the characteristics of my system here just the same way when I reproduce this as I did making the first one. If I happen to change the backing material, all right, that's going to change the way my sandwich goes together. If I happen to change how much pressure I use to create my sandwich, that's going to change my airflow across my surface. So there's a number of different things that can certainly affect the way that this instrument responds to another instrument. I want to maintain that certain level of range, that certain level. I want to maintain that design so that if I have more than one production site, I can provide this device to production site A, and if I have a second system, I can provide that to production site B. And those two mills, if they're producing basically the same product, selling to the same customer, will always have a way to gauge whether or not their system, their production system is working and it's going to meet their customer expectations. All right, so now all of this, as I talked about, all of these details need to be maintained. And what I'm going to do is I've started a table here. And I've input the information, some of the details about the specifics about the Bekk test, the backing, the test area, load pressure, and are we using, how are we creating that differential pressure from low pressure to a high pressure. In this particular case, as I mentioned, we're using a vacuum, so we can create that situation where we have an area of low pressure and an area of high pressure and actually see some air movement and be able to measure the rate of air movement across that surface. After watching this video, you should have a good foundation moving forward in the series. Like always, we enjoy helping our customers. If you have any questions, please don't hesitate to contact us because our goal is to help you make better paper.